Hi everyone, this is our MAE 152 project analyzing the iPhone 6s and the case.
The iPhone 6s frame structure comprises a chassis made from 7050 series aluminum alloy, a screen made from ABS polycarbonate, and a battery consists of copper and 1060 aluminum alloy layers. The first static analysis is to model the phone being tested using a bending test machine. The first iteration has a 1mm sidewall thickness. The maximum stress is concentrated at the sidewall near the bending force and the hole cutout, and is below the yield stress of the materials, so a linear analysis is valid. For the second iteration, the sidewall thickness is increased to 1.3mm to improve the rigidity of the foam. The lowered maximum stress is now located at the edge of the hole cutout. In the third iteration, the sidewall thickness is further increased to 1.7mm. The improvement in the results is consistent with the design changes. The second static analysis is to model a person storing the iPhone in the back pocket and sitting on it. The stress and the displacement results improve in the progression of the iterations. In the third iteration, the maximum stress is decreased by only about 2%. A modal analysis is performed to see whether the resonance frequency of the structure coincides with the taptic engine's frequency. All three iterations perform well, with the first mode being much higher than 200 Hz. The third type of analysis performed is a thermal analysis to see the effect of the battery's operation on the frame. The maximum stress in this analysis is significantly lower than those caused by the static loads in the previous analyses, and the temperature did not exceed the maximum operating temperature. The stress in the second iteration decreased significantly by 83.7%, and there is a slight improvement in the results for the third iteration. The second thermal analysis performed simulates the effect of wireless charging. The second and third iterations see a large decrease in the maximum stress compared to the first iteration, and all three iterations had the temperature below the maximum operating temperature.
Our iPhone 6s case has an ABS PC material. For static structural analysis 1, the bottom edge of the phone case is fixed and the sides have rollers to simulate the effect of sitting on the phone case while it is in your back pocket. The yield stress is 57 megapascals, while the maximum stress is 15.454 megapascals, resulting in a minimum factor of safety of 3.688. The maximum displacement is 1.57 millimeters and the mass is 0.07 pounds. For the second iteration, the iPhone case has twice the thickness in the walls. The maximum stress decreased to 4.745 MPa and the maximum displacement decreased to 0.265 millimeters. For the third iteration, the design is changed to a model a charging case in which the bottom portion is thicker. In this iteration, the outer walls were also thinner and have curvature that do not allow for the exact same boundary conditions, thus reference geometry was used. We believe that this is the reason for such extreme changes in the results and possibly invalid results. Nonetheless, the maximum stress is 78.024 MPa, which is above the yield stress. Therefore, the results are definitely invalid under the linear assumption as the part yields. The maximum displacement is 21.88 millimeters and the mass is 0.16 pounds. For the second static structural analysis on the first iteration of the phone case, fixed boundary conditions are placed on either end and a 20-pound force is applied on the middle of the case. The maximum stress of 32.85 megapascals occurs around the volume button holes and the maximum displacement is 3.47 millimeters. The factor of safety is 1.74. For the second iteration, the maximum stress decreases to 14.14 MPa and occurs in the same region. The maximum displacement decreased to 0.86 millimeters and the factor of safety is 4.04. For the third iteration, the maximum stress decreased from the first iteration but increased from the second iteration to 15.986 MPa. The maximum displacement of 0.354 millimeters is smallest out of all and occurs higher up the phone case, where the thickness decreased. Thus, this design change has the best combination of results for low stress and displacement for this analysis. A modal analysis was also conducted on the phone case to compare the first mode resonant frequencies of each iteration to the taptic motor frequency of 200 Hz, to ensure no complications would occur. This first mode occurs at 563, 1042, and 1276 Hz respectively for the first, second, and third iterations. Thus, each iteration is safe from issues resulting from the vibration of the motor. For our closed-form solution comparison, the phone case is modeled as a beam with simply supported conditions. The hand calculations predict a max displacement of 0.29 millimeters compared to the 0.947 millimeters calculated by SolidWorks. This error can be attributed to the walls and base of the phone case not being geometrically perfect beams.